So I heard this morning, this Algebra Qual question, and I was trying to help, but I don't think my method works. I realized a critical flaw in it. But somebody else in the chat gave a really neat proof, and I realized the neat proof gives actually a pretty clever lemma that you could just use. So I thought I'd make this video. Maybe it'll help that person who was studying for his algebra quals, where I'm going to go over this field lemma that was essentially proved by someone in chat, and then show how to use it to solve this problem. So let's start with the lemma. The lemma is this: if f of x is irreducible over the rational numbers with prime degree, and L is a number field of degree m over q with p not dividing m, then f of x is irreducible over L. And the argument's actually very simple. It's a very, I think it's a great argument. You just draw the field tower. So because f of x is irreducible, we can form this field by adjoining a root of f of x. So we can form a field extension, and we know that this will have degree p. And then we can compare, say, with the field extension L, which will have degree m, which is not divisible by p. So let's say m is here. And then we can talk about the compositum between these two fields, which will be L of alpha, because you just add in alpha. So what do we know? Well, we know the degree of the compositum will be of degree at most mp. That's just a fact about composita of field extensions. It's not too difficult to show. And so what does that mean? Well, whatever the degree is here between these two fields will have to be something which divides mp over m, because you divide out here. So let's call this d, and we know d divides mp over m. Well, if it divides mp over m, that means it has to divide p, which means it is 1 or p. And you suddenly see you're running out of a lot of options. That basically say the answer is 1. If the answer is 1, that means L equals L alpha, and alpha was in L. Well, that can't be the case, because if alpha was in L, then you could essentially form the field extension this way, and you would have p divides m, but m is not divisible by p. So that means the degree has to be p. But if the degree is p, that means alpha must be irreducible over L, because you're just taking what you would quotient out by to form L of alpha is you'd quotient out by a factor of one of the irreducible factors of f over L. And so if the degree d, we've argued that the degree d must be p, then your irreducible factor has degree p, which means it's just the entire polynomial f of x. It's not some proper factor. And so that's a very short proof that gives you this pretty neat lemma that if f has prime degree, then you can start from irreducibility over q, and you can bootstrap it to irreducibility over L for all of these number fields, as long as p does not divide L. So let's do it. Let's solve this problem. Solving the problem. Can I copy this? Command C, Command V, great. So solving the problem. So the first thing we notice about this problem is that it's monic. And so when our polynomials are monic, we can just do everything over fields. Like this polynomial will be irreducible or reducible over q and q of I, if and only if it is irreducible over z and z of I. And so then we can use a thing called Eisenstein's criterion to notice that this polynomial right here is irreducible over the rationals, because 2 divides all these things, but 2 squared does not divide this. And so by Eisenstein's criterion, which I had forgotten about because I'm not taking algebra quals, means this is irreducible over q. So f of x, I want to go back to black. F of x is irreducible over q. So then what do we want to show? Well, we just apply our lemma. And the way to think about this is we draw our field tower again, math BBQ of alpha, and L, which in this case is Q of I, math BBQ of I. And what do we notice? This guy here, degree 5. 5 is prime. And this guy here, degree 2. 2 is not divisible by 5. And so already by our lemma, which you could prove within a qual exam, this lemma tells you that F is irreducible over Q of I. And if F's irreducible over Q of I because it's monic, it's irreducible over Z of I. And that's it. The problem's done. And I thought this was just a neat problem, and as somebody in K-Theory's chat who came up with this argument, which the argument was essentially this lemma, but like specialized to this case. And I thought it would be neat and maybe helpful. The only thing I ask is that if you found this useful, I'm trying this new audio setup, and so if there's anything wrong with it, if it doesn't sound great, let me know. If it sounds good, also let me know. Anyway.